So look at the following. Let's say I want to determine 1 squared plus 2 squared plus 3 squared plus dot 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 plus 10 squared. I have a way of condensing all this into a very interesting notation. Since this is a sum of terms, I'm going to use a notation that stands for S, sum. However, we will not use the Roman letter S. We're going to use a Greek letter because it's more suitable for what I'm trying to do and for the notation. This is still stands for the sum. It's still S, but it's the Greek letter S. Why? Partially because Greeks invented it, and secondly, because it has, I have to write what it's called a lower limit. Let's say in this case, I can use I, J, K, there are other options. I equals from the first term. How much is the first term? Where do I start? The answer is 1. And where does it go? Up until 10. That is the upper limit. And inside here I have I squared. First of all, how do I read this? Let's read this together. The sum of I squared from I equals 1 through 10. So how do I get from here back here? When I is 1, I have 1 squared. The sum symbol says plus. When I is 2, then I have 2 squared. The sum says plus. When I is 3, then I have 3 squared. The sum says plus. Dot, 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 plus. When I'm done with number 10, 10 squared, and that's it. Okay, I want to look at a few examples. We are on page 752. Find each indicated sum. For example, problem 32 on page 752. We are given the sum. Now they want I, they use I. We can use any other letter. I to the third. Find each indicated sum. Can anyone give us what does this represent? First, let's take a look. What does it represent? How will I write it?
1 cube plus 2 cubes plus 3 plus 4 cubes plus 5 cubes.
So it's 1 plus 8 plus 27 plus 64 plus 125. How much? How much? 225. Anyone can confirm? 225?
Yep.
Very good. Good. I like to look at the graphing calculator with this for a second. So there is something that is called sum of the sequence. Sum. Second, don't do anything till I figure it out here for 1 second. So second and capital, please wake up or wake up, wake up. Doesn't want to. Some reason it's on strike. I'll probably have to kill this software. Yeah, I have to go to the task manager and kill this program. Okay, and task. Okay, let's see now. So second and catalog. Okay, forget it. Waste of time. I'm not sure why. I probably have to reboot the whole thing. Okay, so let's go to second and catalog. And I want to look at the sum. Okay, if you press on S, yes, here's your S. And then go scroll down to sum, S-U-M.
How do you get to F?
It's right here in blue. S, where and natural log is. So it's in blue or in yellow, depending on what you have. So the sum, next sum, second and catalog at the bottom, 0. Then I go back to second and catalog, and again I press on S because I want the sequence, S-E-Q, right here. So sum of the sequence, the expression is I cubed. So I have x to power 3. And then comma. And I have to have x because x is the variable. And then comma. From 1, comma, to 5, comma, with a scale of 1. And close 2 parentheses.
How did you get comma?
Right here. This is the comma, right here. And press enter. And now I believe you. You said because you said 225.
What do you mean scale of 1? Like 1, 2, 3, 4, 5?
Go from one to the other. Yes. Yes. Yep. So let me write this down for you. So it's a sum sequence. In parentheses, in this case, we have x cubed. The variable is x. From 1 through 5, go through each and every one of them. Don't skip. Close 2 parentheses. So if you want to, you don't have to. If you want to check with the graphing calculator, you can in this way. Okay, so let's look at 42. Another example. The sum from I equals 1 through 5, from I plus 2 factorial over I factorial. These are the factorials from last time. Okay, so can anyone dictate? Do not perform any calculations. We want to see what the terms are with no shortcuts.
One plus
1 plus 2
2.
factorial over 1 factorial plus
5, 1,
These can go up 2.
2.
2 plus 2 factorial over 2 factorial plus.
3.
Very good. Plus 2 factorial over 3 factorial plus
4.
plus 2 factorial over 4 factorial. And finally, the last one, 5 plus 2 factorial over 5 factorial. Very good. 1 plus 2 is 3 factorial is 1 times 2 times 3. I should write it in the correct order. 3 times 2 times 1. It doesn't matter. Over 1 factorial, which is 1, plus 2 plus 2 is 4. So 4 times 3 times 2 times 1 over 2 times 1 plus 5 factorial. 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. Bear with me. I know you can go ahead if you want to with a simplification. That's fine. 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1. And finally, 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. Yes, you can put in the calculator with the sum of the sequence if you want. Okay, here's what I do. 2 and 1, 2 and 1. 3, 2, 1, 3, 2, 1. 4, 3, 2, 1, 4, 3, 2, 1. 5, 4, 3, 2, 1, 5.321. The first one is perfect, plus. The second one is very good, plus. The next one is very good, plus. The next one is plus. Good. 30 plus 56. 30 from here and 56. Good. So then what we have, so this is 50 plus 56 is 106. 106 plus 6 is 112. And 112 plus 12 is 124. Express each sum. We're going backwards now. Okay, so one more time. So we did the factorial notation, and this is the summation notation. And then we have a couple of examples here, and this is it. Now we want to go backwards. Let's say problem 50. We are given 1/3 plus 2/4 plus 3/5 plus dot 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 plus 16 over 16 plus 2. And they want us to write it condensed using the summation notation. This time, let's use J. It doesn't matter. J equals 1 till what? Till how much?
16.
Exactly. 1, 2, 3, dot, 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 16. Perfect. So then the top would be? Very good. J indeed. What about the denominator?
I squared.
There is no square here. Oh, I have 3, 4, 5, 6, up until 16 plus 2.
Another sum symbol,
No.
3 through 16.
No.
Sure.
Very sure.
Just all of the symbols that are there.
What do we have in here?
J plus 2.
Very good. So now let's check all terms. When J is 1, 1, 1 plus 2 is 3. Perfect. When J is 2, 2, 2 plus 2 is 4. Perfect. When J is 3, 3, 3 plus 2 is 5. Perfect. Dot, dot, dot. When J is 16, 16, 16 plus 2. Awesome. Let's look at another problem. Please choose if you'd like. They are on page 752 from 43 through 54. One more time, 752. Okay, I'll pick. Let's say 52. And we have 1 over 9 plus 2 over 9 squared plus 3 over 9 cubed plus dot, dot, dot plus n over 9 to the nth power. What index would you like to choose? You want K, you want J, you can use I. Which one? Now let's say K this time. From K equals? How much? From K equals? 1. Till K equals? Very good, awesome. So there must be a fraction because all of them are fractions. What do I have at the top?
K.
Very good. What do I have in the denominator?
9 to the K.
9 raised to the K power. Awesome. So let's check. When K is 1, I have 1 over 9. When K is 2, I have 2 over 9 squared. When K is 3, I have 3 over 9 cubed. When K is n, dot, 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 when K is n, I have n over 9 to the nth power. Awesome. Any questions? Okay. Finally, let's talk about sequences. Sequences of numbers. A1, comma, A2, comma, A3, comma, A4, dot, 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 comma, AN. This is a finite sequence of numbers. Why is it finite? Because I didn't put a comma, dot, dot, dot. It doesn't go on forever. It goes from the first term of the sequence till what is the last term of the sequence? N, right. Also, AN is called the general term of the sequence. A sequence can be given to us using the general term or a formula that we call a recursive procedure or formula. Let's stick with this for a moment and let's look at a few examples. Write the first 4 terms of each sequence. So we are looking at problems 1 through 12 on page 752. Write the first 4 terms. Any preference? Or I pick? I pick? Yes? Okay, I'm going to pick 10. AN is what again? A sub n or AN is the general term. We are given 3n divided by n plus 5. So we are asked to find the first 4 terms, meaning I have to find A1, I have to find A2, I have to find A3, and I have to find A4. But what does this mean? When I'm told to find A1, I am told actually n is
1.
perfect. When I'm asked to find A2, I'm really told indirectly that I have to write, and so on and so forth. Can anyone give us the first term of this sequence?
3/5.
Very good. 3 times 1 over 1 plus 5.
6.
So 3/6 or 1/2. Is that clear? Yes? Okay, the second one. 6 divided by 7. 2 plus 5. Good. What about the next one? Initially, 9 divided by 8. Okay. And the last one, 12 divided by 8. I'm sorry, it's 9. I will simplify by 3. So this is 4/3. Very good. Awesome. Do we need another example like this one? Yes?
Yes.
Okay, very good. So let's say 6. Unless you want to pick AN, which is again what of the sequence?
General term.
Yes, negative 1/3 raised to the nth power. So they want us to find A1, A2, A3, and A4. Can anyone dictate A1?
1. 1/3. Negative 1/3.
Awesome. Can anyone dictate A2?
Negative 1.
Say it again. 1/9 indeed. When we square a negative number, we always get a positive number. Very good. A3, negative.
7. Negative 1/3.
Very good. Awesome. And the last one?
Was
Yes? 1 over 3 to the 4th is 9 times 9, which is 81. Very good. Last thing. Yes, please. Any questions? How many?
Is it all this for?
It's asking, the problem was asking for.
Oh.
Yes, this particular problem was asking the first 4 terms. Okay, and now, last thing, and not new more, not more after the beyond this, no more new stuff. In the previous example, we were given the general term. Sometimes the general term cannot be determined, but a relationship between the previous term can be determined. So for example, on the same page, I'm looking at problems 13 through 18. So the sequences in these problems are defined using a recursion formula, something that repeats. So write the first 4 terms again. They're asking us for the first 4 terms. And let's say we look at 17, and then you choose the next one. We are given A1 to be 4, and we are given AN, which is the general term, but you will see it's not a clean cut. It's twice times AN sub n minus 1 plus 3. And we are told for n greater than or equal to 2. So, let's go back to the sequence for a moment. A1, comma, A2, comma, dot, 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 comma, AN minus 2, comma, AN minus 1, comma, AN plus 1, and if I want to continue, I can. So this is the relationship. This is not a clean general term like we had it here. It did not involve other terms of the sequence. It only involved a number and n, which has to be in the problem. The same thing here. This general term did not involve other terms. It only involved n. Here, as you see, how do I read this? Any term of the sequence is twice the previous term of the sequence plus 3. And I am given the first term. So I have to find A1, A2, A3, and A4, but I am already given the first one. So now the question is, how do I find A2? How do I find A2? 2 minus 1 is A1. 2 times A1 plus 3. So this means 2 multiplied by 4 plus 3, which is 11. Now, can anyone dictate A3? What should I write for A3 for everyone to see what I'm doing? I have to copy the 2. I have to copy the previous term of the sequence, which is very good. And I have to add 3 to the answer. 22 plus 3, because I have to multiply first, is 25. And can anyone dictate the last term, the 4th term that we need to find?
2 times 25 plus 3.
2 times 25 plus 3. So this will be 50 plus 3 is 53. So we learned, this is the last thing we needed to present. So we learned that sequences can be given nicely, plainly, as the general term. Don't forget your question. And the second way of presenting a sequence is when I don't have the general term, but I have a general term that depends on the previous terms of the sequence. Mark?
No question, just a bigger question.
Oh, okay. Good, so let's look at another problem. Let's say 18. And we have A1 equals 5 and AN equals 3 AN minus 1 minus 1 for n greater than or equal to 2. In other words, I cannot plug in 1. in this relationship. That's all it says. And this is the end of the material. Find particular terms of a sequence from the general term and use recursion formulas. So this is all done now.
Is that -1?
Yes.
Okay.
This one is -1, but it's a suffix, and this is -1 as well. Yes. We are asked the same question to present A1, A2, A3, A4. Can anyone give us A1?
A1 is 5.
Good. Can anyone give us A2?
3
First
times
step, so for everyone to see.
3 times 5
Yes?
-1.
Good. Indeed. 15 minus 1 is 14. Perfect. Yes. 3 times 14 minus 1. And this is 42 minus 1, 41. Correct me if I'm wrong. And the last term that we are asked to find, we can find as many as we want. But the last one we are required to would be
3 times 41 minus
3 times 41 minus 1. So 123 minus 1,
122.
that's it.
What's the point of putting n is greater than or less than?
I cannot plug in 1. 2, 1 minus 1 is 0. There is no A0. Is that clear? You cannot plug in 1. You have to start with 2.
I mean, it gives you 5, so.
What do you mean by 5? This is A1. When n is 1, the answer is 5.
Okay.
So you cannot plug in here 1, because A0 does not exist. Is that okay?
Technical problem, do they have to give you A1? They don't give
Yes,
you a starting
yes. They could give you A3 and say, they could give you the third term or something that they want to ask you to start somewhere else. But it should be the first term.
Yeah, like,
Yeah.
what if they give you A3 and they want you to find A1, you just don't have to?
Depending on the relationship, you could have that question. There is a sequence like that. It's called Fibonacci sequence.
So we don't have to do that.
No, it's not. No, that is mainly used. I shouldn't say mainly. One of the applications is in the stock market. The Fibonacci sequence. Okay. No, you're not going to have to do that. Good. That's all I had to say this semester. But I have to go back to the exponential decay functions. So let's go. This is a review. But actually, I didn't do a problem, and Tim is right. So we are on page 530. Let's look at problem 30.
What section is this one?
4.5, page 530. 4.5, applications with exponential and log functions. Last section in chapter 4. 4.5, applications. Okay, so let's read the problem. The half-life of aspirin in your bloodstream is 12 hours. Take notes when I read. Half-life, 12 hours. How long will it take for the aspirin to decay to 70% of the original dosage? Decay to 70% of the original amount. Okay, now this problem does not give us the model. I will give you the model. Okay, although we know there are 3 models that are pretty similar. So because we're talking about mass, I'm going to say m of t equals m0 times e to negative rt. Your book may show this, which is the same thing. I like to use mass because we're talking about decay. I don't like to use amount, but it doesn't matter. It's the same model. This has the same significance, is the initial value. This has the same significance, is the radioactive decay rate. This has the same significance, is time. In this case, time in hours. Okay. So let's talk about first about the half-life. What does this mean? It means that if I have right here, this is the amount of aspirin. This is my M0 that I take right now. I take this, and it's aspirin. I know that in 12 hours, this amount in my bloodstream will be half. Good. Can anyone give us an ordered pair that just presents what I just said? One more time. Let's do this again. I take the aspirin right now. I don't know. I can't tell you how much I took. But I know for sure that precisely in 12 hours from now, in my bloodstream, there is half. Half of it decayed and dissipated, gone. But I still have half of it. Can anyone give us an ordered pair that when I plug it in the function, it will make sense? Say it again. What will be the x-coordinate? The x-coordinate will be?
1.
Very good. Time, 12. Very good. So 12 hours from now, how much will I have in my bloodstream? Half of, awesome. Half of what? Look carefully at the model. Half of what?
100.
Half of, we don't know that.
100%.
Half of the original amount. Can anyone read the original amount? Exactly. M0 divided by 2. One more time. Let's do this again. This is very important because this is the starting point, and this will help us solve the whole thing. So one more time. Right now, I take this amount of aspirin. I don't know what it is. I know it's M0. It's the initial one. I took it. And 12, exactly precisely 12 hours from now, I still have in my bloodstream half of it. So 12 hours is the time independent. How much I still have aspirin in my bloodstream? Half of what I took. I don't know how much I took. I don't know. But I know for sure that I'll have half. Good. Now I want to put this in the function. Tell me slowly which portion goes where. Say it again. Exactly. This piece is M0 over 2. Of course. Equals. M0. Very good. E to minus. Do I know R? No. Good. Times. Awesome. So you understand what we did? So when time is 12, the function is M0 over 2. Clear? Perfect. What do you think I'm going to do now? Look at this equation and think and say, oh, I know. You are going to, say it again? No. Divide by? I want to divide by something that it cannot be 0, and I don't have. Exactly. That's the trick. Divide both sides by M0. The left-hand side is 0.5. The right-hand side is e to negative 12r. Because it's an exponential equation, I have to get rid of it. And it turns out that I can. Because it's the same quantity on both sides. And it's not 0. What do I do now? Yes? Yes. The only way, because 0.5 and e cannot be presented with the same base. I have to apply natural log to both sides. Awesome. The left-hand side is natural log 0.5, ln 0.5, and the right-hand side is negative 12r times natural log e, because I'm bringing the power in front. Only log allows me to do that. But how much is natural log e?
2.1.
Okay, we forgot. Let's take it on the side. So I should write here times natural log e. I bring this in front times natural log e, correct? Good. Natural log e is a number that I don't have, but I know that this is equivalent to an exponential equation. What is the base here? I don't even see a base. What is the base of ln? E.
That's one.
E, exactly. E raised to what number is E? E raised to what number is E? 1. That's why I don't have to write it. Natural log E is 1. So finally, I have the radioactive decay rate. How much? What do I do to both sides? Very good. Natural log 0.5 over negative 12. I can do this by hand. Nobody can. So let's go. Oh, this is dead. I forgot. Oh, it woke up. 0.5 divided by, in parentheses, negative 12. And close. So, please use 4 decimals. For the growth rate or decay rate, please use 4 decimals. 0.0578. 0.0578. Now I can go back to the model. M of t equals m0e to negative 0.0578 t. What did I just do? Nothing much. I only determined the exponential decay rate. Okay, I'm going back to my notes. Let's see what does the problem want from me. How long it takes to decay the amount that I took to 70% of it, not half of it, but to 70%. So I know that I take it now. In 12 hours, it will be 50% in my system. I want to know when it's going to happen that I have 70% of the original amount in my system. So will it be more than 12 hours or less than 12 hours?
Less.
Of course less, because if we get to 50% in 12 hours, we get to 70% in much less. Good. So now, can anyone give us the ordered pair that we will have to plug in? I'll help you with x coordinate. But I want you to give me the y coordinate. And just remember, let me read it one more time. 70% of the original amount. Perfect. Awesome. 0.7 M0. Absolutely. 70% of M0 is 0.7 times M0. Good. Now tell me how to plug it in the model, and we will be able to determine T. Slowly, carefully, how do I put the ordered pair in the model? 0.7 M0 is the left-hand side, equals, I still don't have it, E to minus 0.0578 times T, because I don't have it. Okay, what type of equation this is, and what do I have to do first? I'm not moving M. I am dividing both sides by M0. Very good. Then the equation is 0.7 equals e to negative 0.0578 t. I know how to proceed. How do I proceed? Yes, awesome. Natural log indeed. So natural log 0.7 equals negative 0.578 t times natural log e. Bless you. How much is natural log E? 1. So finally, t equals natural log 0.7 negative 0.0578. One more time. Do I expect an answer smaller than 12 hours or more than 12 hours? Smaller than 12 hours. Okay. So natural log 0.7 and divide everything by negative. I'm just going to put the negative and I'm going to recall the previous answer. And press enter. As expected, in 6 hours and 0.17 of an hour. So I take one more time. I take right now an unknown amount of aspirin. I know that 12 hours later I will have half of it. From that information, I was able to determine the radioactive decay rate. And then I was able to answer the question, how long it takes for 70%, for 100% to decay to 70%, not to 50%. So all we did was we put this particular point in the problem, 0.7 M0 equals M0. As you've noticed, the initial amount that I took of aspirin doesn't make any difference. Very good. Other questions for me? Other questions? Okay, I would like to start reviewing with these handouts that I gave you some time ago. Okay, there is nothing here for this test on this one, on this color. Okay, let's look at the green one. Yes, we have a lot here. We have 1, 2, 3. Three here. 4, 5. So let's start from the beginning. It's a lot. Here we have a lot to look at. If you'd like to skip any of this and you know it, we can skip it. So we can accomplish as much as, so we accomplish tonight as much as possible.